Değerli katılımcılar, değerli dostlar, TÜBİTAK'ın tüm sosyal medya platformları üzerinden bizi izleyen, bilgisever, bilim dostu değerli insanlar. Bu seminerimiz çok güzel bir güne, Ramazan bayramının 1. gününe denk gelmiştir. Ben de öncelikle herkesin Ramazan bayramını içtenlikle kutluyor, ülkemiz ve insanlık için sağlıklı ve mutlu günlere, hayırlara vesile olmasını diliyorum. Seminerimiz İngilizce gerçekleştirilecektir. Bu nedenle İngilizce devam edeceğim. Hello and welcome. Welcome to TÜBİTAK Research Institute for Fundamental Sciences, to the wonderful case of our interdisciplinary seminar series, which we organize for national and international audiences to minimize the negative impacts of COVID-19 situation in the world on scientific thoughts and science-based actions. Now, it is my distinct pleasure to introduce you our very special speaker, Professor Tanja Bosak from Massachusetts Institute of Technology, MIT. She has kindly agreed to join us for this seminar, and she will give a very special talk entitled Mars 2020, Exploring the Red Planet with the Perseverance rover. Tanja Bosak is a professor of geobiology at the Department of Earth's Atmospheric and Planetary Sciences at MIT. Professor Bosak's laboratory uses experimental geobiology to explore modern biogeochemical and sedimentological processes in microbial systems and interpret its record of life on the early Earth. Professor Bosak was born in Croatia and graduated from the Zagreb University with a degree in geophysics. After she moved to the California Institute of Technology in Pasadena, where she studied signatures of microbial processes in ancient sedimentary rocks and earned her PhD in geobiology in 2005. She also spent 2 years at Harvard University as a microbial initiative postdoctoral fellow. And in 2007, she joined the Department of Earth, Atmospheric and Planetary Sciences at MIT. Professor Tanja Bosak's research efforts have been recognized by many awards, among them Subaru Outstanding Woman in Science Award from the Geological Society of America, James McIlvaine Medal from the American Geophysical Union, MIT Harold Edgerton Faculty Achievement Award, and Simon's Early Career Investigator in Marine Microbial Ecology and Evolution Awards. At this point, I want to thank once again Professor Tanja Bosak for joining us for this seminar. We are really looking forward to it. Over to you, Tanja. You're welcome to begin your talk.
All right, thank you. Thank you for inviting me. It's really a cool opportunity to present even virtually to the Institute in Turkey, because I'm starting a collaboration with one of your colleagues. I don't know if she's here yet, Nurgül Balsi. So you'll see there are some places in Turkey that have a lot of relevance to the current exploration on Mars, and I hope to tell you about that. So I'll start sharing my slides. All right. I hope you can see all that. And please, if anyone has any questions during the talk, maybe just turn on your microphone and yell out, because I can't see everyone. But feel free to interrupt, or if you don't understand something or I say some word or just get into the jargon too much, just stop me and ask. All right, so I will tell you about this exciting exploration that has begun in February, the exploration of Mars and the search for the collection of various samples, including those that can collect, maybe sample some biosignatures, by the Perseverance rover. And so this is the artist's rendition of what the rover will do. And one of the major differences between this rover, the Perseverance rover, and previous rovers on Mars is that this rover will drill samples of rocks and prepare a cache to eventually be returned to Earth that then we can study and analyze in all sorts of ways. And so this is one of the major goals of our mission. And the reason to go to Mars is it's drawn our attention for really many decades and even centuries, in part because it's our closest planetary neighbor. It's really the closest planet to Earth. And when people started looking at Mars with ever better telescopes, they noticed features that are present on the surface that tell us that Mars has not always been this red, dead, and dry planet. And so here is a beautiful image from the Viking mission. So this is from the 70s. The Viking orbiter made an image of what we know as the Mars surface. It's full of craters. It's full of craters, meaning there hasn't been an atmosphere shielding the planet from impactors for a long time. It's a very old surface. The numbers of craters and their sizes tell us about the great age of the surface. And in places where the surface is the oldest, meaning there are many craters on top of craters on top of craters, people also noticed in these images these channels that seem to start somewhere a little higher and then drain into some of these craters. You can see some of these edges of the craters are very degraded, meaning perhaps some erosion that is not happening in the younger craters. So that told people that Mars's surface, at the time these craters were being made, contained water, which tells us about a planet. Today, Mars is about minus 60 degrees Celsius average temperature. Nothing can be liquid on the surface of Mars. Even if water, by any chance, if there are places where temperature exceeds 0 degrees Celsius, the atmosphere is so thin that that water cannot be stable. So the liquid cannot be stable. It goes straight from ice to vapor. Mars's atmosphere is very, very thin, I think 6 millibars. So here is what we can do now with these samples I mentioned. So some of the major mission objectives of for the collection of these samples are geologic exploration. Just like every other mission previous to the Perseverance rover mission, we do want to look at this ancient environment of Mars because we landed in Jezero crater, which is one of these craters that has a channel and has some deltaic deposits. We want to understand processes by which water, when it was present, meaning a warmer, very early Mars, we want to understand processes that formed rocks and perhaps altered them by processes by which this water interacted with minerals. We also want to understand when all that happened, which is the main reason to collect samples that can be dated. When there was water, when was the crater made itself, when did the delta deposition stop? So that can provide some major constraints on how long the water was even at the surface and when exactly that happened. And then, because I'm a geobiologist, to me, the most exciting goal, and probably to most of the general public, the most exciting goal for some of these samples is to collect samples that are most likely to preserve evidence of former life. So any samples that have the potential to contain organic matter, some samples that maybe even have macroscopic structure. So this is about 5 centimeters or so. Any samples that tell us maybe there was something organic that was binding sediments and making them cohesive would be nice to see in the field. But even if we don't, we can go after certain mineral assemblages and certain types of deposits that have a high potential of preserving either organic matter or biosignatures. And the two are not necessarily the same. And I'll go a lot more into that. And so the rover, once we use all of the instruments on the rover to identify these types of rocks, will be making our way out of the crater, preparing a returnable cache, and that cache has to contain samples that sample the real geologic diversity of the environment. So it won't be just one type of sample. It'll be really different types of samples that serve to address different scientific goals by the generations and really hundreds and thousands of future scientists who will have access to the samples once they are on Earth. So maybe some of the graduate students listening to this can apply to study some of the returned samples. I'll tell you a little more about the timeline for this. And then one of the goals of the mission is also, you may have heard about the instrument MOXIE, and the instrument, it's really MOXIE and the collection of the regolith sample that have the goal of preparing for human exploration down the line. So can we really know what the dust is like? What kinds of hazards do we have to prepare for? And also, can we generate enough oxygen, enough fuel on the surface of Mars to perhaps bring people, if they go to Mars, we can bring them back. So there were some demonstrations of just technology that were involved. So here's the rover. It's about vein-sized. So here's the scale, 0.5 meter, and it has this arm that's extendable. The arm contains a lot of instruments. So all of these boxes are different types of instruments. That's the ground penetrating radar, for example. There are many, many cameras on the rover. There is this arm that can come really close to the surface of the rocks and examine them by Raman spectroscopy for minerals and especially for organic matter. There is a really nice, almost like a hand lens camera. There is also pixel planetary in situ lithography spectrometer. So it's like an XRF that maps small areas. So it can tell us what kinds of elements are present really in small, maybe 2 centimeters by 2 centimeters patches of the rocks. And in this arm is what's the most important thing for us, the drill. So the drill that can drill into the rocks, and then the samples of rocks and also soils will be deposited in the belly of the rover, where there's a wheel with a lot of sample tubes. So here is just to illustrate the international nature of the rover. There are various instruments. You can see some flags. So there are French instruments. So the Raman unit on the SuperChem is French, for example. Rimfax is made by Norwegians. There are a lot of JPL made instruments. MEDA, the atmospheric components, are Spanish. And so there are a lot of different international team members here. And so this just gives you the idea of where these different parts are. And really most of the weight of the rover, most of the space on the rover is dedicated to the sampling and caching equipment, which is not what previous rovers had. So here is why Jezero. So I told you a little bit about all these craters that have some inflow channels, meaning the water carved its way to deliver sediments into some of these craters. And here is, so if this is Mars, here, the values, these colors, what they show you are the relative heights. And so the Martian surface is actually really uneven. It's hemispherically dissimilar. So the lowlands are in the north and they're very low. There are kilometers. You can see these are in meters. So there's about almost 9 kilometers of difference between the Martian north and the Martian south. So all of these southern highlands are very red and yellow, meaning standing up high, and that's the older terrain. That's where the craters are. And we can count them and say, oh yeah, it's been a long time since this surface was made, and then the craters had a long time to impact it. So here is this area that is amplified here. So there is this big impact basin. There was a big crater, Isidis, but at the rim, there was a smaller crater called Jezero crater. And here is the orbital image of it. So it's a crater that's about 50 kilometers, 45 kilometers in diameter. And from the orbital imagery, people recognize this inlet valley that deposited sediments and created this feature that based on some geomorphological, some finer resolution images, told people here the sediments were delivered over a period of time, so not just by a catastrophic flood, and made this feature called the delta. And here's the outlet channel. So eventually the water level actually breached through the rim, and some of that water flew out. So there was some flow through the lake at certain points in time. We don't know what points exactly, but we have an estimate just based on the size of the crater that this crater impact was made about 3.8 billion years ago. But that's one of the major goals of the mission, to figure out when it all happened. The idea is it's all dry, cold, dead now. But at some point in Gezero's history, there was liquid water filling it up and even flowing through the crater, delivering sediments, and perhaps the conditions were habitable, and perhaps even there was life in there. And so here's more on the context. Not only do we see these features, just geology that tells us about the former presence of water, but the mapping of minerals, spectroscopic vis-IR, so visible in infrared mapping from the orbit, tells us about certain types of minerals. It's more sensitive to certain types of minerals. And so all of these false colors indicate certain spectral bands that are detected. And so the green to blue indicates the presence of carbonates, which is what forms reefs on Earth. So this excited people a lot. You can see that they're particularly concentrated along the edges where the shorelines would have been. There is orange, which is olivine, which is really just the basalt forming mineral, one of the basalt forming minerals that is really common in all of these highlands that surround Jezero. So the idea is that a lot of that olivine was probably delivered, particularly in the delta and around, from this flow of water with the sediments, and pyroxene as well. So these are some mafic minerals. These are some igneous types of minerals, but there are a lot of clays. So there's certainly a lot of clay material in the delta. So clays hydrated, we even see hydration signals from space, both in carbonates and in the clay minerals in the delta, meaning water was interacting with all of this original material. So we want some samples of that to see how it all happened. And here is the path of the estimated flow. So it came through this channel here and kept delivering sediments to the delta into different lobes. And the extent of the delta is thought to have been much, much greater in the past. So this is only what's preserved today. It probably extended. Actually, we don't quite know, perhaps even all the way to all of these smoother outlines. So yeah, that is when I talk about the delta, I'm referring to this region. And here is where we landed. And I'll stop here. And I just want to go again. I never get sick of showing and watching the landing site, the landing video, because it's just beautiful. All of these cameras that we for the first time had pointing up and down and really active during the landing showed some amazing footage and also told us something about the landing site. So I will start sharing my screen with the video. Here we go. And I won't go through the entire thing, but this is the deployment of the parachute.
Has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 430 meters per second at an altitude of about 12 kilometers from the surface of Mars.
So this is my favorite part. So you see the heat shield getting dropped. So that just landed somewhere else away from the rover because of the atmospheric friction. This is my favorite part, when you see the red planet getting bigger and bigger and bigger and closer to the rover.
At an altitude of about 9.5 kilometers.
So now we see some rocks and a lot of that red dust that covers the surface of everything on Mars. And you can see some of the features getting closer to us. There are a lot of craters. You can see that it's getting rougher.
3.3 meters per
and here we are. So that's the delta. And you will recognize this bone-like feature with 2 craters later. So really, we now have footage from space from closer up, than much closer than the orbital imagery.
The initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
So you can see that the terrain is actually different. Here it's much rougher and it retains craters. Here there don't seem to be many craters. There seem to be some linear features. So we don't really know what we are looking at. And this is one of the questions about the landing site still. So this entire bone-shaped structure seems to retain some rough material that doesn't retain craters. And here's the delta. We had an internal bet placed on the team, so people were able to go to the map and predict where the rover will land. So whoever got the closest, I don't know if there was an award, but at least she got the bragging rights.
We have completed our terrain relative
So,
navigation. Current speed is about,
yeah, you can see some of the polygonal material starts showing up. Now we are really close. And so now watch how the dust gets moved away by the rockets, because the rover has to shoot at the surface to not crash. So it really descends by that. And so there's the sky crane. It gets lowered. The rockets are active. You can see all of this light material is getting blown. And so some rocks get actually lighter because they get dust on top, and some rocks get darker because the dust is removed. And so that is it. And the descending stage goes away. This was very, very moving. So anyway, I never get tired of this video. And so that happened on February 18, and we were at the surface. We knew exactly where we were within maybe an hour or less. And this is where we landed. So this star, now you see the delta and the crater, and this is exactly where we landed. That is that bone-like structure. The rough terrain here, the craters in this also rough terrain here. And this is the landing site. So the first images started coming along. And this is one of the panoramas. These have been publicly released, and a lot of people actually are playing and assembling panoramas. Actually, some of them do have more time and do a better job than we can do on the team. These are just enthusiasts who love to look at these images. And so just to mark some features, so this was one of the first panoramas. So the rover can rotate the camera and take images 360 degrees around. And here is just to orient you in space. So this is some of this terrain that retains craters to the east of the rover. This is the delta. We can even see crater rim in the distance. The delta is a couple of kilometers away from us. Crater rim is about, I think, 8 or 10 kilometers away. So this is really the entire crater rim. And here are some delta remnants. So little chunks of the delta, most of the stuff in between got eroded, but some of these delta remnants remained. So just to orient you. And here are some images of the landing site. All of these rocks, it's full of rocks. It looks like Mars. It's not particularly shocking, but we, to this day, still discussing whether these rocks are igneous or sedimentary, because we haven't been able to move much from the landing site yet, mostly because we had to have another technology demonstration. So first of all the instruments needed to be turned on, verified, calibrated. It takes a while, and every single command to the rover takes a day. You send a command, everything goes well, you wait for data, the next day, maybe 2 days later, you can plan something else. So that takes time, but we had another technology demonstration, which I think you probably heard now about. It was very successful. Ingenuity Mars helicopter did a number of flights, increasingly more complex. And again, this is just a technology demonstration to show that we can fly drone-like vehicles, drone-like craft on Mars. And eventually these types of craft will be used to maybe do remote geology, really fly over terrains where the rover can't go. For example, some of this rougher material and really image it. And so really just like people use drones on Earth, this will one day be possible on Mars. But the idea for our mission was not, it was just really to see whether this can work in the first place. So the helicopter was not designed to last a long time. But now finally, we are about to depart from the landing site and start exploring. And so here are the main tasks. We need to explore the geology. We need to see what we are looking at, understand more about how things happened in a sequence in time, whether, for example, the delta was deposited on top of this rough terrain, or maybe some of these terrains were in place after the delta was maybe even eroded. And we need to start making our way from the landing site in a certain, so we'll go a little bit further to the south, wait until we can drill, and then start moving fast to the north over the delta towards the crater rim. And so that will take quite some time. It's a long game. It is planned to take, so just for the rover to understand the geology, collect about 18 samples or 20 samples, and get to the crater rim will take 1.5 Mars years, which is about 1,000 sols, which is roughly 1,000 Mars days. Or so it's about 3 years. It's a long time. So it won't be, the rover can only move so fast, and also we have to do all this science. And so the plan for the rover is to collect about 18 samples, and there are some controls, blanks for organic preservation and contamination that will be collected before the rover gets out of the crater. And that will result in the first sample depot location that will be somewhere within the crater itself. And the reason for this is that the rover lifetime, all these things designed and built, and the guarantees that they will last are only so far. So the guarantee for the rover lifetime by the engineers is 1.5 Mars year. But these rovers tend to last actually a lot longer. If you look at Curiosity, it's been roving happily along what is now almost 10 years after it was launched. So during the extended mission, if things go well, and after this first sample depot is deposited, the rover will get out of the crater to incredibly old terrain that we don't even have any samples from. And that may take another 1.5 Mars years, so another 3 Earth years, and that will be after the prime mission, and collect more samples of the terrain that is beyond this rim. And so here is just a notional, just an example of a potential trajectory for the rover now. So this is the landing site here, and we will actually move a little further south and look at all of these terrains. So both this rough stuff that doesn't have craters and the stuff that has craters, collect maybe some samples, and start moving fast north. This is actually smooth driving. And within 1 year, make it to the delta, collect more samples. So all of these points that are in red are some types of samples that may be collected in different places. So parts of these rough terrains, parts of crater retaining terrains, maybe some delta deposits, which I'll say why that's exciting. We'll start making the way across the delta. I mean, this is all notional. Don't expect the trajectory to look exactly like that. This is all subject to what we see on the ground and what the team decides to do. And finally, make our way towards this, to me, probably the most exciting material, because these are carbonates, and make its way out of the crater. And so that will result hopefully in about 10 unique, actually 14 unique samples, but some of them will be doubled because the rover will leave some in this primary depot, but then take some from the crater as it makes its way out and keep them and then add to them some other samples that are of material that's outside of the crater, so not really sedimentary material. And so with that, I will talk about some samples that I'm most excited about because they give us the opportunity to ask for the first time if there was life on early Mars. So here is the surface. This crater is more than 3.7, 3.8 billion years old. And the water was present in there maybe at 3.7, 3.6. We don't know yet, but really early on. And that is older than any sedimentary material that we have on Earth. And gives us the opportunity to ask when life emerged, whether life emerged, or what the conditions were in which life could have emerged. Because we have water, we have a rocky planet, we have probably a climate that can support liquid water. So everything should be habitable. And we also know that there are a lot of impacts at that time. There are a lot of craters that should have delivered some of the necessary ingredients for life to the early planets. So let's go and sample. So what do we sample? And before that, I will just tell you, this is really the current understanding of the evolution of prebiotic chemistry in early life. So here's the estimated age for Jezero and the activity of water in it. You see these question marks, meaning we don't really know. It's roughly here, but these are huge error bars. We are talking about multiple hundreds of billions of years plus and minus. And so here is what we think, or what we know or don't know about how life evolved. So on Earth, we know that there was a stable hydrosphere. We need water, we need liquid water, and we know there was some on Earth about 4.2 billion years ago, just from minerals that are still preserved from some sediments, but not entire sedimentary rocks. We just don't have anything this old. And then the idea is somehow some prebiotic chemistry, meaning a set of reactions that produce very specific compounds that are needed by living cells, proteins, nucleic acids, lipids. Some of that chemistry starts taking place, probably in a disorganized way. Some of that chemistry also contributes to the making of information molecules such as DNA, RNA. Some of these molecules can self-replicate, meaning they just take over, they just keep making more of themselves. Some metabolism evolves, and that eventually leads to cellular life. Now, we have no idea how this really happened. The best way to assess this is currently done experimentally in some chemical laboratories. We have no idea how long it took. I mean, here I have this spread out over 400 million years, but we have no idea. It could have been very fast, and then we suddenly have cellular life. Or maybe cellular life came from somewhere else. So we really don't know. What we do know is that on Earth, we have the first indication of cellular life in some sedimentary rocks. So these are silica-rich cherts that preserve. So here's, this is about maybe a couple of millimeters long. So the light stuff is silica, tiny granules of silicon dioxide that was deposited in seawater. And these dark materials are organic, rich, former remnants of current remnants of former microbial mats, because all of these curls seem to have been flexible and bendable. We know that this material, whatever it is, there are still some little carbonaceous domains in there. We know that it had to have been bent, what else bends and is present in shallow water systems. So we know there was some cellular life present by 3.4 billion years ago. So all of this, the dark ages, a big black box that now we can go and explore actually by going to another planet, which is Mars. So here are just some summaries, or here's the current knowledge of what it takes to even make prebiotic precursors. We know some amino acids, a lot of them are in fact present on meteorites, carbonaceous chondrites, probably on comets as well. But some of the more complex molecules do need specific conditions to be preferentially synthesized. So not just to get the mess that is present on meteorites, but really controlled set of reactions that lead to a controlled selective set of products. And so here are, so people are doing these kinds of experiments in test tubes. I mean, these are serious organic chemists who are doing this. So what they start from are some materials that can be plausibly present in meteorites or delivered to the surfaces of planets. So this is hydrogen cyanide, SO2, a volcanic product. What they find is they need minerals, they need iron, they need copper, they need also sulfur to catalyze the reactions. And importantly, they cannot get this to happen. They need a series of reactions that concentrate products or reactants. They need to increase sometimes the molarity of compounds. And so the best way to do that is to either freeze dry or freeze and really concentrate components in the liquid, or evaporate, meaning surface conditions. So not hydrothermal vents, but surface conditions. Another major requirement for these reactions, and actually this has been experimentally shown to make nucleosides and actually nucleobases and lipids. Don't worry if you don't know what these chemicals are. I had forgotten my organic chemistry, but this is amino acids, lipids, and nucleobases. To select for some of these, we really need UV light, which turns out to destroy certain things and really help the production of others. Again, meaning surface conditions. And here we are in a lake that was open to the surface and received sunlight. So there's no better environment to explore. And so here's just to tell you, this is one of the plausible sources of organic material. So a lot of organic initial compounds are present in meteorites. For example, this is a carbonaceous chondrite. And so big picture questions that we have for the samples are, what are the sources of organic matter on Mars? Were the organic compounds made by live prebiotic, or how were these, if we find something organic, how was it made? Are there maybe even fossils? What was the carbon cycle like? How did this organic matter cycle? Was it all just what we find in meteorites, or was there something different? And so the objective for us is to acquire samples that really have the most likelihood of preserving organic matter. And for Earth or Mars, we have to do it by going to fine-grained clay-rich deposits where bedrock, so something that we really can place in some stratigraphic sequence, know when it was deposited in time and in relation to other rocks. We need to sample that. And on Mars, in particular, we need to go and look for mudstones because they have demonstrated widespread potential to preserve both organic matter and fossils on Earth, so microbial fossils. We are looking for microbial life because nothing before 3 really, it took a long time for anything on Earth to get macroscopic and complex. So really, if at best, we can hope for microbes. Also, importantly, mudstones already in Gale Crater have been shown to contain organic matter. And so here is Gale Crater, the Curiosity rover, which has a gas chromatograph mass spectrometer, and it made its way from the landing site and saw a lot of mudstones. And in some of this, so this is really, it's currently even further out, but a lot of mudstones sampled on the way and analyzed by mass spec. This is what some of them look like, not like much, but these flat lying deposits. And the Curiosity rover found some of these types of compounds in these mudstones. When it drilled, this is actually an actual selfie. And in these rocks, which are really dark underneath this red surface, there are some compounds that really can be explained by any other way, no contamination, but they seem to be indigenous organic compounds that are present on Mars. So we know we have a hope of finding something. Now, why claim minerals? This is where we go on Earth to find the earliest signs of life. And here are some examples. Here are carbonaceous particles, meaning something that used to be organic, Now it's just really goopy globs of material that are preserved in these 3.2 billion-year-old shales. So fine-grained, clay-rich deposits. Also carbonaceous laminates, so we can see entire layers that are enriched. All of this dark material is organic. So we have high hopes of finding mudstones. And we need to, you can see all of these are thin sections. To see any of that, unless we are really lucky and hit some organic rich vein, we need to collect samples and bring them to Earth. And only then can we analyze the organic material for its isotopic composition, ask how the material is distributed, because look, all of these particles, the dark grains, are on scales that are smaller than 10 microns. We cannot investigate those types of scales with a rover. And then if we find organics, the molecular structure and what's really what they are can only be addressed by the really most sensitive mass spectrometers on Earth. So a lot of reasons to bring materials back. And then I mentioned the other exciting type of sample, which are carbonates. And on Mars, unlike Earth, so on Earth, we have limestone. You probably have a lot of limestone in Turkey. And, but on Mars, it's not limestone, it's not rich in calcium. The carbonate minerals primarily contain magnesium, which again, this is an example from Turkey. There is a lake, Lake Salda, that is in basaltite terrain, ultramafic terrain. And because a lot of cations such as iron and magnesium are leached out of those terrains, and not so much calcium, these cations can be concentrated in these evaporating bodies of water and result in the precipitation of entire, well, microbialites, stromatolites along the shorelines, just like what Jezero has. Remember, I told you that the carbonates, magnesium-rich carbonates, are distributed where the shorelines, around where the shorelines would have been. So there's something intriguing about the distribution of these. And if the Jezero carbonates contain precipitated magnesium carbonate minerals, we also have a high hope of preserving or looking for biosignatures and collecting them. These minerals can tell us also a lot about what the atmosphere was doing, because they're carbonates, they sample some of the CO2 and so on. So a lot of curiosity about these. So here is, again, just a map. So really we have to make our way. So this is year 1, year 2. We will really only make our way to these in year 3, but something to look forward to. Year 3 is, yeah, it's a long time. So, and also for the mudstones, we do have, we have some of these delta remnants that should be surrounded by the low-lying mudstone, like flat mudstone deposits. And here is just a recent photograph from a camera of one of these remnants that is close to the delta. So this thing in the distance is the delta that seems to have cross bedding and all sorts of stratification that tell us this is really one tongue of the delta that was protruding and just got eroded. And so we have hopes of maybe finding mudstones around these types of deposits. And then during the extended mission, the rover will make its way along all of these ultramafic and mafic terrains. And we really don't know what we are looking at. These are some of the oldest planetary materials anywhere, not sedimentary, but planetary. So we can really hope to answer a lot about the evolution of Mars and other planets, because again, we have no such materials from Earth, and including the evolution of Mars's climate. These materials will be able, because they're igneous predominantly, so volcanic rocks, will be able to even address the question of when and why did the climate change. So really thinking about Jezero, but looking at the outside, because about 4 billion years ago, Mars was warmer and wetter, today cold and dry. And one of the major reasons why this is, well, probably something in the atmosphere that was blanketing the early planet and keeping it warm went away. And one of the major mechanisms by which planetary atmospheres are thought to be protected are their dynamos. So the idea is we have a star all these planets revolve around our star, the sun, and highly charged particles constantly impinge upon the atmospheres. And if a planet has the magnetic field, so this is the dynamo, all of these field lines, they actually deflect the solar particles away from the atmosphere. Now, if the magnetic field, this dynamo, goes away, the solar wind impinges just more directly onto the atmosphere and strips it off, just kicks off really light elements that are volatile. And this is why Mars is thought to perhaps have lost its atmosphere, at least the leading theory. And so the history of the atmosphere and the climate is really tied to the history of Martian dynamo. Why and when Mars had a magnetic field, and when did that change? And so here's how we know that Mars must have had a dynamo. Actually, this was recognized even the early 2000s when people from an orbiter at 400 kilometers altitude measured the strength of the magnetic field. So this is how it's mapped. These magnetic field values correspond to something at the surface that would be comparable to places on Earth. So while Mars does not have a changing, doesn't have a North Pole, you can see all of this plus and up and down is distributed somewhat randomly, but it seems to magnetize rocks in this manner. We do need a dynamo at some very early point in Martian history. And all of these really highly magnetized points actually map to this older part of Mars, the southern hemisphere. So a lot of reason to sample this old terrain. And so the science questions for the extended mission are what characteristics defined the early planetary evolution and habitability in terms of what's in the rocks, how big is the core of Mars, and why and how long can it sustain the dynamo? When did the dynamo go away? Are there some former habitable environments in which water interacted with all of these rocks even outside of Jezero? How long did the Martian dynamo persist? And really, how is the demise of the Martian dynamo tied to the atmospheric loss? And what are the bedrock units that we can use? So really, we need rocks that we can use to date. So once we bring these rocks to Earth, we need to date them, and that will help us really constrain the ages, because I told you the error bars and all of these, just based on crater counting, are huge. So, and then of course, what are the effects of large impacts? Because this is something that seems to have shaped the surface of early Mars and also possibly influenced its habitability. And so I'll conclude here. So the conclusions and plans, we are finally moving away from the landing spot. And so we have begun the Mars sample return campaign, and the nominal plan is to return these samples in 2031. This plan is a coordinated effort between ESA, the European Space Agency, and NASA. So the mission, Mars 2020, our job is to find the best samples, collect them. And that is primarily a NASA effort, but the plan to return samples is now being developed, and it is worked out by both NASA and ESA. They have an agreement, and they're working together and putting money towards that. And so these samples will be returned by, first there will be a depot, the samples aligned nicely in a row or a couple of rows somewhere where it's convenient to pick them up. And then in 2026, the Fetch rover is supposed to be launched to land on the surface of Mars close to the depot. The Fetch rover it has maybe a camera or two, can't move far, has to land really close to the depot, has to pick up the samples and then launch them into the orbit around Mars. And then there's a tricky part of something we've never done before, which is, well, the Fetch rover either, but there's another tricky part that has to happen around 2030. A spacecraft has to be launched, another one, to pick up these samples from the orbit around Mars and bring them to Earth. So it's this rendezvous. If you've seen the movie Martian, this is exactly how the person gets lifted off the surface of Mars, and he has to be picked up by something from the orbit around Mars. So it's really utilizing that's a realistic scenario, and we'll try to test it. So if all goes well, the samples could be on Earth by 2031, but not earlier, and it could be delayed because there are a lot of moving parts. And so the samples can tell us about the history of the Martian climate and magnetism, prebiotic and early biological evolution. We may look for fossils if we can cut thin sections on Earth, planetary evolution, ages of different surfaces, what's in the Martian soil, and that's particularly important for human exploration and so on. So I'll end here and I'll just take questions.
Thank you very much for this exciting and intriguing talk. So now we can pass to questions. We have received several questions by email, and I can ask these questions, address you these questions.
Yep.
And we have also a question in chat button. Can you read chat messages?
Yeah, as the propeller of the helicopter is spinning, the Mars dust is not visible. There's not much dust where the helicopter was. We had to find a place where things are pre-exposed. And actually, the landing site in Gezgini, most of the material, I keep saying dust, but it's not really red dust. It's actually sand. It's like dunes. So it's coarser. So it would not be lifted by the helicopter. You really need rockets to blast things, to like what we saw in the descent video. You really need much more power than a helicopter. What is it? A kilogram and a half. I can't remember exactly the weight of the helicopter itself, but it's a tiny thing. So yeah, we don't have much dust where we are. It's more sand, and also it's really unlikely to be lifted by the tiny helicopter. The question of the ocean, whether fewer craters in the Utopia Planitia. No one quite knows the origin of this dichotomy, and there have been multiple hypotheses about the ancient shorelines and was there an ocean. And actually, there has been quite a bit of mapping done recently, really to see whether they match some global water body, and the idea that's emerging, or really that idea seems to not have held up. So the early Mars would have contained water, but mostly in these fairly disconnected bodies of water. So some streams and lakes, crater lakes, but there's no strong evidence for an ocean. So Utopia Planitia, the question of why there are some flatter areas is a good one. And I don't think we still understand why the highlands are highlands and the lowlands are lowlands. But certainly there's a lot of younger dust or sand material that has been moved to those lowlands because, sand grains do travel downward and then get deposited.
So the first questions sent by email is there any chance to find any form of life without carbon, hydrogen, oxygen, or phosphates? A sub-question, can life somehow emerge from non-biomolecules?
We do, well, once we have the samples on Earth, we don't have currently search patterns, meaning we don't even know how to look for that kind of life that is not carbon, hydrogen, oxygen. So we certainly would have a hard time looking for something like that by perseverance. Although, when I ask people what these kinds of biosignatures would be, they're like, well, if you see a jumbo jet on the surface of Mars, then that tells you there's some life. Clearly, it's too complex. And I'm like, yeah, there are multiple dead rovers and one currently living apart from Perseverance. So that's sign of intelligent life on Earth that sent rovers to Mars. But the idea for these samples is once they're on Earth, they will be available to the community. And if any of these ideas are developed to the point that we can look for weird life, yeah, anyone can apply and look at these samples and think about what to even look for. But so far our search, and here's another reason to really not worry about that too much. I think what works in our favor is we know that we get so many meteorites from Mars on Earth even today. And that flux back and forth has been much, much higher in the past because of more impactors, just more things hitting either planet. And so the cross-contamination, the chance for cross-contamination from Earth to Mars is so much higher than having to come up with some weird life that would only live on Mars.
Thank you. The next question is it possible to form a life cycle under Martian conditions in the lab settings? Can we trigger the evolution processes on Mars in this way?
Yeah, indeed. And so some of these experiments that I showed, I just summarized them, but some of these test tube experiments, people are trying to really, well, they're done by organic chemists that are really just trying to make reactions work. They're thinking really hard about the reactions that give you multiple products. And also they're trying to match the conditions. So they're trying to not just say, oh, this takes place in a crazy solvent and something that you could never expect on Mars, but they're really trying to match it to, what if I have this mineral that I know is present on the surface of Mars? Or what if we have this kind of temperature or this kind of UV flux? So there are efforts to do that, yes. But it takes a lot of people and it'll take time. I mean, we just started making progress in that area.
Mm-hmm. Do you think does transport on Mars play any role for sustaining life? Can water vapor transport above Jezero crater be a sufficient resource?
No. Not today.
Do we expect to find fossils or bacteria?
Do we expect? This is what people will be looking for. So I don't think we will find, because yes, bacterial fossils are tiny. Unless we find structures like what I was showing from the Turkish lake, something that is a big colony, a big film of bacteria that was colonizing a surface and then making a rock. Unless we find that, which would be extremely lucky, we will have to really cut thin sections and people will be looking using the best microscopes to convince themselves that there are some fossils. But yes, if they look for fossils, they'll be looking for bacterial fossils.
Could tardigrades left on Mars possibly adopt there and sustain life?
No. I mean, tardigrades, you could transport them to Mars and they would probably do fine for, 10 years, 100 years, I don't know, especially if they're covered by a little bit of rock, but they wouldn't form an active biosphere. They need to eat something. Tardigrades are animals and there's no active, vibrant, hydrological, and also organic cycle on Mars. Everything seems to be in big stasis. So yeah, unless you put a tardigrade in some, I don't know, old organic rich rock, which also we should be so lucky to find that. Yeah, I don't think so. Yeah. And I'm sorry, I'll have to stop here. Please email me questions if you have more questions. I have to go and give another talk. So I have to join the other meeting, but it was so nice to. Thanks for all these questions. They're awesome.
Thank you very much for this talk again. So we can stop here, no problem.
Please, and yeah, feel free to email me. I'll try to respond to more questions.
Yeah.
This is great.
Okay.
Thank you. Bye.